Welcome back. We're going to start chapter 3 today. First topic for this section 3.1 is maximum and minimum values. There are a couple of definitions. First, I'm going to talk about those. We say for a constant c in the domain of a function f of c, that means the y value corresponds to that x value. So if you have an x value of c, corresponding y value is called the absolute maximum value of f if it has the largest y value among all the other y values. We similarly say that y value is this absolute minimum if it has the smallest y value. So this notation means the f of c, which is the corresponding y value to x value of c, is less than or equal to all the other y values. So the absolute maximum and absolute minimum means the largest and the smallest y value possible among all the y values. We can say local max and local mean. Local max and local mean basically is the maximum not overall but in a small area. We say f of c is the local maximum if it has the largest value in a small neighborhood around c, so somewhere near c. And similarly, local minimum would be the local minimum value would be the y value where it's the smallest y value among the y values nearby. But this is locally, you look at those y coordinates, and absolute value, absolute max and absolute mean means you look over overall graph and see where is the maximum y value, where is the minimum y value. Okay. After introducing this, maybe it's easier to see it through a graph. When they mention value, you always think about the y value. They ask you absolute maximum or absolute minimum point, that means write a coordinate, write the x and y coordinate. So here's an example. If we look at this graph that is defined over an interval, the domain is from 0 to 5. This is the domain, starting from 0 all the way, the x values are only in this section. You're not allowed to go to the left side. Endpoints is closed, but here you have an open circle on the right side, so this endpoint must be an open circle. So the domain of this function is simply 0 to 5 with open parentheses at 5. It means 5 is not included. And how do you find the domain? Is by the projecting. You project a graph on the x-axis and you find the domain. So here, if we look at the maximum y value, where is the maximum y value? The maximum y value happens to be, if you look at the graph, the point that has the highest y value happens to be this location, star. And if you look at all the y values, that is the highest y value. So I will say this point, x is 1 and y is 3. This is, you write it not that way, but like as a point. This is the absolute max point, not the value. If they ask you for what is the absolute maximum value, that means only we care about the y value. You write 3. This is the highest y value possible. How about the absolute minimum? Absolute minimum value, the value here, means look at all the values on the graph and figure out what is the smallest one. If you look at the graph, the point here has the smallest y value, but it turns out that point is an open circle. That means that point is not included. You cannot say a point, how about this point close by? If you pick that, then I'll go a bit closer. So we really don't have any point close by to compare with. And you cannot pick any other point. If you only discuss this point, that means that is not acceptable since it's not in the domain. If it was a close point, then you would consider it as an absolute minimum. In this case, since we cannot accept that point, we'll say no absolute minimum. If I make it a close point, then that point 5 and -2 would be the absolute minimum point, which means the y value in -2 is the absolute minimum. How about local? local max and local mean. I'm going to write points for these so we see the coordinates. Okay, let's look at the maximum points. Turns out this is the star has the highest y value among all the y values in this neighborhood. That star is a local maximum. If you look at 4, this is at that point 4 and 1 has the highest y value. Therefore, that is another point that we should consider. It's only you look at the neighborhood around 4. You don't look overall. If you look at around 4, what is the highest point is that point. If I look at around 3, what do I see is smallest y values in this area happens to be a 3. The local maximums happen at 1 and, sorry, let me change the color. Happens to be at 1 and 3. And the other one is at 4 and 1. This is the local maximums. And the local minimum happens to be at 3 and -1. Some textbooks consider the endpoints somehow local maximum, but since we don't have the left side, we do not consider the endpoints as local points. So we only look at inside the graph, not the endpoints. Okay, so local max and mean, absolute max and mean, nothing too complicated based on the graph. You should simply find out where those points are. Okay, so here's an important theorem, extreme value theorem. It's something that should make sense. So let's say, what is the extreme value theorem? It says if you have a continuous function over in a closed interval, it's important that you have a closed interval, then f will have the absolute maximum and minimum definitely over this interval. That means if the endpoints are considered, let's say you have 2 endpoints. This is A, and here you have B. If the 2 endpoints are part of the graph, you have a closed interval, and somehow you connect these 2 points with a continuous function, then this function definitely will have a maximum and minimum, and definitely that maximum minimum would be absolute max and absolute min. So here, for example, absolute maximum happens at that location, absolute minimum maybe happens at the endpoint at B, something like that. For our earlier example, since B was open, we couldn't choose B. That's why we didn't have the absolute minimum. But in this case, if we assume that the endpoints exist and belong to the domain, then the function should definitely have an absolute maximum and minimum. That's what it means. That's the extreme value theorem. Easy to understand. We're going to use this idea to find out where are the maximum and minimum. But before I do that, maybe I should mention the Fermat theorem as well. Fermat theorem. This is something that's easy to understand as well. It says if there is a local maximum and minimum at a specific point C, and if the derivative exists at that point, then the derivative must be 0. So think about it. If you have a local maximum and minimum, how does the graph look like at that point? So somehow, let's say you have this graph. If there is a local maximum, like this point, what do you know about the slope of the tangent line? If you draw the tangent line, that's how the tangent line could look like. So what is the slope? Slope is 0. But that point turns out to be a local maximum. That means if this is a local maximum point, then f prime, which is the corresponding derivative, the corresponding slope at for the tangent line, must be 0. If you look at the local minimum, similar thing. The derivative at that point, f prime, must be 0. That means if the derivative exists, it must be 0. But sometimes the derivative does not exist at the local minimum, something like if you have an absolute value function. The derivative at the corners, if you remember, it doesn't exist. It's a breakpoint. So this point, even though it's a local minimum, but the derivative doesn't exist at that point. So we cannot use this Fermat theorem. Fermat theorem is only if the derivative exists, then definitely the derivative is 0. So if you have a local maximum or minimum, And if the derivative exists at that point, then the derivative must be 0. So based on these two, I can say the next theorem is the general one. It says the critical number. Here is a definition. Sorry, not the theorem, a definition. A critical number of a function f is a number c where the derivative either is 0 or the derivative does not exist. That means these two cases that we mentioned, either the derivative is 0 or the derivative does not exist because it's in breakpoint or maybe a discontinuity. If you call this critical number, then this critical number is a good choice to have a local maximum or local minimum. But not always is the case. Sometimes you have discontinuity. If you look at this point, that point does not belong to the domain. So this point would not be in the domain to discuss it. So if the point is in the domain, then that point would be either local maximum or local minimum. So the critical number is just to figure out where the local maximum and minimums are. And if you're looking for the critical number, you find the derivative, set it equal to 0, figure out where the derivative does not exist. That tells you the location for these local maximum and minimum. We do examples now. I wrote a couple of examples to find the critical numbers. So here, two functions. Let's find each one separately. The question is find the critical number for these functions. I'm going to solve first the critical number for the f. The f of x is given 2x cubed plus x squared plus 2x. And they ask you to find out where the critical numbers are. Okay, so we need to find the derivative. Derivative is 6x squared plus 2x plus 2. And we're looking to find out where the derivative is 0 or where the derivative does not exist. This is a polynomial derivative function. The derivative always exists. There is no critical point where the derivative does not exist. So the other choice that we have is to set it equal to 0 and figure out where the critical numbers happen. I'll just figure out where, for what x values this derivative is 0. You can factor out the 2, divide by 2, you will get 3x squared plus x plus 1 equal to 0. You can have, I don't think you can factor this. So let's use quadratic formula. X is minus 1 plus or minus square root of b squared 1 minus 4 times 3 times 1, which is 4 times 1, 12, divided by 6. Okay, so in this case, under the square root is a negative number. Make sure that I wrote the derivative correctly. Yes. So this is where I can say here, negative 11 divided by 6. I can say the derivative does not have any solution because underneath the square root is a negative number. So that means this function f has no critical number. And this means it has a meaning behind this. If there is no critical number, that means since the function has derivatives everywhere, you will never see this shape. Because if that's the case, then there would be a local minimum, which means the derivative at that point would be 0. So since there is no such a point to have critical number, that means the function looks like this. It never has that bowl shape, either from above or below. So you never see this shape or the other side, because you would have a local maximum or local minimum. This was the example where there is no critical number. But here, look at the g function. And we're looking for the critical number again, x to the 4/5. By the way, 4/5, if you don't know, again, This means 5th root of x to the 4th. That's 4/5. What it means. I'm going to write this that since we want to take the derivative times x minus 4 squared. To find out the derivative, g prime x would be 4/5 x to the negative 1/5 multiplied by x minus 4 squared. I'm using product rule, plus x to the 4/5 times the derivative of the other term times 2x minus 4 to the power 2 to the power 1 multiplied by the derivative of inside, which is simply 1. It's by chain rule. You have to follow chain rule. This 1 at the end was the derivative of the inside. The derivative of x minus 4 was simply 1. Okay, so simplify it and factor out stuff. G prime x would be here. They both have x minus 4 in common. Actually, 2x minus 4. And what is left from the first one is 2/5 x to the power negative 1/5. And write it in the denominator as x to the power 1/5. And numerator is x minus 4 is the first term. And for the second term, that is x to the power 4/5 left. You can simplify it a bit more, make common denominator. So let me make common denominator the same line. Common denominator would be x to the power 1/5. X to the power 1/5. And since I have a 5 here, I will multiply 5 here. Okay, so g prime x becomes 2x minus 4 multiplied by 2x minus 8. That's 2x minus 4 distributed, and plus x to the 4/5 times 5x to the power 1/5. You add the exponent, 4/5 plus 1/5 becomes x to the power 5/5, which is 1. So you will have 5x, and the denominator is simply 5 to the power 1/5. Okay, finally we're there. G prime x, the simplified version. Numerator is 2x plus 5x, so 7x minus 8. So you will have 2x minus 4, 7x minus 8, divided by 5x to the power 1/5, which I can write it as 5th root of x. X to the power 1/5 means 5th root of x. So this is the derivative. Now we have to check, we're looking for critical number. Where does the derivative is 0, and where do we have the derivative does not exist? So for that, let's consider both cases. Here is the color. Here I'm going to consider g prime x, where is this equal to 0, or where g prime x does not exist. If I answer to these two questions, then I already figured out where the critical numbers are. G prime x is this fraction. When do you get the fraction to be 0? Is when the numerator is 0. So if the numerator is 0, that means x minus 4 must be 0, or 7x minus 8 must be 0. So it is either x minus 4 equals to 0, or 7x minus 8 equals to 0. And when do you get the derivative to not exist? That means if you're dealing with fraction is where the denominator is 0. If the denominator is 0, then the fraction is undefined. So where is that? That means underneath the square root must be 0. 5th root must be 0. It happens at x equal to 0. Or you can say 5th root of x equal to 0, raise both sides to the power 5, simply becomes x equal to 0. So what we have is the critical numbers happens to be at x equal to 4, at x equal to 8/7, and at x equal to 0. These are the three critical numbers. That means these points are choices to be local maximum or local minimum. That's what it means when you have a critical number. Not always they're going to be the case, but if it happens to be one of these. Sometimes you have a critical number that is not a local max or local min. Let me see if I can, something like x cube. X cube has this point where the derivative is 0. but it's not a local maximum or minimum. That's one of the cases when you see that the derivative actually has no derivative is 0, but it's not the local maximum or minimum. These points that we found, 4, 8/7, and 0, these are candidates to be local maximum and minimum. To be sure about them, you have to draw the graph, make precise graphing, then figure out are they local max or local min. But you can use this idea to discuss absolute max and absolute minimum. How do we do that is, let's say you have a function f and they ask you to find the absolute max and min. There are certain steps you do. Is first, you find the critical number. After you find the critical numbers, then step 2 is find the y values corresponding to those critical numbers. Or the critical numbers, as well as the endpoints, if there is an endpoint. So if there is interval, you find the critical numbers at the endpoints as well, because it's, the y values at the endpoints as well, because it's an option to have absolute maximum and minimum at the endpoints. If you do that, then that means you find out all the y values. The largest y value, the largest y value is the absolute maximum, and the smallest y value would be the absolute minimum. This is if you're dealing with functions that do not have like vertical asymptote. If you remember, vertical asymptotes would happen to be something like this. You'll have a graph that has, in this case, you would not have a absolute maximum or minimum, because around the vertical asymptote, the y value is increasing toward infinity. So those points will show up as critical numbers, but they would not have any y values, since they're not going to be in the domain. So always follow these steps if you're looking for the absolute maximum and minimum. So let's do it for these two examples. Okay, we're looking for the absolute maximum min for this function f of x, square root of x divided by 1 plus x squared over the interval 0 to 2. So first step, find the derivative. So we're looking for f prime x. Take the derivative of the numerator. It's gonna be a bit messy. So I picked the hardest examples. So you guys have seen the difficult one. The other ones seem to be very easy. So here the derivative of numerator is 1 over 2 square root of x. I skip some steps. You can write it as x to the power 1/2 and take the derivative. Multiply by the denominator of 1 plus x squared minus numerator times the derivative of the denominator. Denominator derivative is 2x. All divided by 1 plus x squared. By the way, the domain of this function in general is all real numbers. But in this case, only you're given over the interval, all positive numbers, plus 0. In this case, you only focus on the interval 0 to 2, because specifically they mentioned find the absolute max and mean in this interval. If you simplify this derivative, what you get is, I'm going to get rid of this square root in the denominator. I'm going to get rid of this square root, 2 and square root. So what do is, I will multiply everything by a square root. I will multiply 2 square root of x to this term, 2 square root of x to this term, as well as 2 square root of x in the denominator. By doing this, I can cancel out these two. So what do I have is 1 plus x squared. 2 times 2x would be minus 4x. Square root of x times square root of x becomes square root of x squared, which is simply x, times 4x becomes 4x squared. and denominator is 2 square root of x times 1 plus x squared squared. This is a simpler form of the derivative. And 1 plus x squared minus 4x squared is 1 minus 3x squared divided by 2 square root of x 1 plus x squared squared. Okay. So here we found the derivative. Second step, find the critical numbers. What are the critical numbers? So step 1, step 2. Where do you get the derivative equal to 0 is where the numerator equals to 0. So I'm going to find the critical number by setting the numerator equal to 0. And where do you get the derivative? This is where f prime x equals to 0. Or where do you get the derivative to be does not exist is when the denominator equals to 0. But the denominator is only 0 in this term, because 1 plus x squared is always a positive number. You'll have no solution for 1 plus x squared. So it happens only when square root of x equals to 0, or simply saying x equals to 0. Okay, so derivative, how about where the derivative equals to 0 is add 3 divided by, subtract 1 divided by 3 and take a square root. So x would be plus or minus square root of 1/3. These are the critical numbers, x equals to 0 and x equals to plus or minus square root of 1/3. But here's one thing that you should notice. If you go look at the domain the function is picked, there's a different highlight here. That was a mistake. Okay, so if you look at focus on this interval, the interval is chosen to be 0 to 2. And if you look at the critical numbers, 0 is already there, but square root of 1/3 positive part is acceptable. The negative one is not in the given domain. So I cannot accept this negative sign. So I only focus on the solutions that belong to the domain. In this case, the plus is the only critical number I care, as well as 0. So these are the critical numbers in that domain. Not all of them, but the ones in that domain. Step 3, I need to find the y values. This was actually part of step 2. Find the critical number and their y values. Yeah, sorry, I made a mistake. This was first the derivative. This whole thing was the derivative and find the critical numbers was step 1. And step 2 would be to find the y values. I'll find the y values correspond to the critical number. X equals to root 1/3 and x equal to 0. Then endpoints are 0, so I don't need to rewrite it. X equal to 2 is the other endpoint. I'll find the y value. What is the y value? How do I find the y value? Is you go back to the original function. What is the original function? It's square root of x divided by 1 plus x squared. If you replace the endpoints, if you replace 0, what you get is 0. If you replace 2, you'll get square root of 2 over 1 plus 2 squared, which is 5. So you'll get y value is 0 and 2 divided by root 5. If we replace 1/3, square root of 1/3, you'll get square root of, let me write this a bit lower. If you replace square root of 1/3 into the original function, which is f of x equals square root of x divided by 1 plus squared. And what you get is, sorry, this was root 2 over 5, not 5. Sometimes I make these mistakes. Be careful. You'll get square root of 1/3 divided by 1 plus 1/3 squared, which is 1 over 9. So you'll get 1 plus 1 over 9, which is 10 over 9. You can multiply the 9 in the numerator and denominator and simplify. So you'll get 9 times that divided by 10. Okay. So now here I ask you, this was step 2. Step 3. By the way, you should turn this into a decimal number first to figure out what is this number. and compare it with this. Because it doesn't look like it's that clear which one is smaller, which one is larger. But I can answer one question. Absolute minimum. Which y value is the smallest between all these three y values? It happens to be 0 because the other ones are positive. So 0 is the absolute minimum value. How about absolute maximum? Calculate these two, figure out what are the decimal values for each. I feel like this the first one is larger, so I will say 9 square root of 1/3 divided by 10. I feel like that one is larger. I assume, but you should calculate. Definitely calculate to see which one is larger. Okay, so this tells us the absolute maximum and absolute minimum for this function. We can do another example. I wrote another one. The other function is trigonometric function. Gx is given t, sorry, g of t supposed to be g of t given t plus cosine t over 2 over an interval 0 to pi. Here, let's say g of t given t plus cosine t over 2 over the interval 0 to pi. Pi was an open parenthesis. Okay, so first let's go through this procedure. First step, find the derivative in critical numbers. G prime of t would be 1 plus derivative of cosine t half would be sine negative sine t over 2 multiplied by the derivative of inside. The derivative of t over 2 is simply 1/2. 1/2. Okay, this is kind of easy to see. T half derivative would be, you can write it as 1/2 times t derivative. Just simply 1/2. So this 1/2 is the chain rule to the derivative of the inside. So g prime t is, let me write it simpler, 1 minus 1/2 sine t over 2. Okay, the question is, what are the critical numbers? Sine is always well defined everywhere. So the domain for the g prime function is every real value. It doesn't really have any restriction. So there is no point where the derivative does not exist. The derivative is well defined. So we just need to figure out where the derivative is equal to 0. I'll set it equal to 0. Okay, so if we want to solve this, you'll say 1 equals 1/2 sine t half. Multiply both sides by 2. We'll get 2 equals sine t half. Now you might ask yourself, where do I get sine to be 2? If you remember on the inner circle, sine is the corresponding y value. The y value ranges from 1 to -1. You will never have a y value of 2. It's never possible. There is no corresponding y value that gives you sine to be 2. This guy has no solution. What does it mean? It means no critical number. Kind of important that you find the derivatives correctly. Otherwise, if you forget that 1/2, you might find multiple solutions. Okay, so no critical number. So what now? We look at the endpoints. What is the endpoint? The endpoints and critical numbers, or the step 2 was the y value of the endpoint. X was 0 and x equal to pi. So corresponding y value, we need to find out the corresponding. I replace 0 into the original function. The original function was g of t was t plus cosine t over 2. If you replace 0 here, you'll get 0 plus cosine 0, which would be 1, so you get y value of 1. If you replace pi, you'll pi plus cosine of pi half would be 0, so you'll get y equals to pi. Cosine of pi half is simple. So now if I ask you, step 3, where is the absolute max and what is the absolute minimum? You should say absolute maximum happens to be y value pi because it's around 3, larger than 1, and absolute minimum happens to be 1. This would be the answer. Only if you focus back on the question tells you that the endpoint 0 is acceptable, but the endpoint pi is not acceptable. That means if you get a solution through this endpoint, you cannot accept that. So it means y equal to pi. This is not possible since it was not in the domain. So I cannot accept this solution. So what can I say about the absolute maximum? No absolute max. That means when you graph this function, at 0, you have y value of 1. And the function increases toward pi here and pi here. Function will kind of increase toward that. It's an open circle at the end. But there is no local minimum between, and you will have only one absolute minimum. And it happens to be at 0 and 1. The absolute maximum was an open circle, so it's not acceptable. Okay. This was just to make sure that you look at the domains and make sure that the endpoints are acceptable. Every other example is very similar, much easier than these two. Okay, I'm going to stop at this point, and next time we will move on to 3.2.